Richard Feynman was bored stiff in physics class. He'd already worked through the textbook, the homework, the lot. So his teacher, a bloke named Mr. Bader, pulled him aside one day, slid him a book, and pointed to a single equation. And Feynman said that moment changed how he saw the universe forever. Here's what's wild though. That equation Mr. Bader showed a teenage Feynman sits in textbooks today. Universities still teach it. But almost nobody, and I mean nobody, will tell you what it actually means. Because the moment you ask the right question about it, physics breaks. You're watching Curious Physics AU. Today, we're cracking open the Feynman Lectures and pulling out the one problem your physics teacher quietly walked past. Let's get into it. Picture young Feynman, bored, restless, scribbling in the back of a Brooklyn classroom. Mr. Bader notices, walks over, and instead of giving him detention, he hands him a calculus textbook and says something like, "You're not using your brain, kid. Here, work through this." And then he points at one principle, just one. It's called the principle of least action. Now, don't switch off on me. I know that sounds like something out of a uni textbook with a $40 price tag, but stick with me, because what's actually buried in this idea is one of the strangest things in all of physics. Here's the basic version, in plain English. If you throw a footy from one end of the oval to the other, it traces an arc through the air, right? Up, over, down. Newton's mechanics tells you exactly why. Gravity pulls it down, your throw gives it speed, you crunch the numbers, you get the path. But there's another way to figure out that exact same path, and it's bloody weird. Imagine every possible path that footy could have taken. Straight line through the air, a massive loop, a zigzag, anything you can draw between where you threw it and where it landed. Now imagine you could attach a single number to each of those paths, a score. The number is called action. Don't worry about the maths, just think of it as a kind of cosmic energy budget for that path. Here's the spooky bit. Out of all those infinite possible paths, the one the footy actually takes is the one where that number, the action, is the smallest. The universe, somehow, picks the most efficient path every single time, without fail. That's the principle of least action. And the moment you really sit with it, your brain starts to itch. Because how does the footy know? How does a chunk of leather and air with no eyes, no calculator, no Google Maps find the cheapest path before it's even taken any of them? It gets worse. This isn't just for footies, it's for everything. Light works this way too. Pierre Fermat figured this out 400 years ago. Light going through water bends, right? Refraction. The reason it bends is because the bent path is the fastest one from A to B, given that water slows light down. Light somehow takes the path of least time, like it knew. Throw a ball, fire a bullet, drop a brick, watch a planet orbit the sun. All of it follows the same rule. Minimum action, always. This is in the Feynman Lectures, Volume 2, Chapter 19. Feynman literally writes that this principle blew his mind as a kid, and he never got over it. He says it's deeper, more fundamental than Newton's laws. So here's the question every uni student should be screaming. How? How does the universe know? Does the ball try every path first? Does it have foresight? Is the future somehow reaching back to tell the present what to do? And here's where every single physics lecturer in every uni on every continent suddenly finds something else to talk about. Because the honest answer is nobody fully knows. But Feynman, and this is where it gets fair dinkum mind-blowing, Feynman thought he had a clue. Here's what young Feynman did with this problem. He asked a question that, frankly, sounded mental at the time. What if, he said, the particle does try every path? What if that footy, in some sense, took the loop and the zigzag and the straight line and every other path you can draw all at once. In our everyday footy on an oval world, that sounds insane. But Feynman wasn't talking about footies. He was thinking about electrons, photons, the tiny stuff, the quantum stuff. And in the quantum world, strap in, that's exactly what seems to happen. Feynman's big contribution to physics, the one that won him the Nobel Prize, is called the path integral formulation of quantum mechanics. And here's the basic idea, stripped to its bones. A particle going from A to B doesn't just take one path. It takes every possible path simultaneously. Each path has a little quantum wave attached to it. Most of those waves cancel each other out. The weird, looping, zigzagging paths interfere and disappear. But one path, the path of least action, the one classical physics predicted, is where all the waves line up and reinforce. So that's the one you see. Read that again, slowly. The reason a footy looks like it takes one path is because at the level of atoms, it's quietly trying every path, and they nearly all cancel out. Reality, at the deepest level we've ever measured it, isn't a single line through space. It's a smear of possibilities, a weighted vote. The world you see is the one where the universe agreed with itself. This isn't science fiction. This is how every modern particle physicist actually does the maths. The path integral is built into the standard model. It's how we predict the behaviour of electrons in your phone screen right now. But here's the bit that breaks people. The bit no uni course wants to land on. If the particle is trying every path, what's doing the trying? Because there's no little engine inside an electron checking the books. There's no quantum GPS. The particle doesn't know anything. There's just the wave function. And the wave function, somehow, encodes every possible history of that particle. Some physicists look at this and shrug. It's just a calculation tool, mate. The maths works. Don't worry about it. That's called shut up and calculate. And it's the official party line in most physics departments. It's why your lecturer skips the philosophy bit. But other physicists, and Feynman was sort of one of them on his moodier days, look at this and say something far stranger. They say, maybe the universe isn't a single timeline. Maybe what we call reality is more like an average, a consensus, a path that emerges because all the other paths cancelled out. And if that's true, then how does the ball know which path to take was the wrong question all along. The ball doesn't choose. Every path happens. We just see the one that survives. Now think about what that means for you. Right now, sitting there watching this. Every electron in your body, every photon hitting your eyes, they're not following a path. There are some over every path they could have taken. Your existence, in a real, mathematical sense, is the leftover after a vast quantum cancellation. That's not philosophy. That's the maths. And that's the problem no university dares to teach. Not because they can't, because once you take it seriously, you stop being able to talk about objects moving through space the way our brains want to. You stop being able to draw little arrows on a diagram and call it physics. You have to admit that the universe, at its core, doesn't really do things going from here to there. It does possibility. So why doesn't this turn up in your standard physics course? Two reasons, and they're both pretty human. First, the maths is brutal. Path integrals require functional analysis, and it'll cook your brain if you've not done the prep. Most undergrad courses just don't have time. So they teach you Newton, then Lagrangian mechanics, then they hand wave at, and there's a deeper formulation called least action, and they move on. Second, and this one's the real reason, there's no satisfying answer at the end of it. Universities like to teach you stuff that resolves. Forces have causes, particles have positions, equations balance. The principle of least action, taken seriously, doesn't resolve. It tells you the universe is doing something, exploring every option, weighting them, summing them up. That doesn't fit any picture you can draw. It just is. And that makes lecturers nervous, because students ask follow-up questions, and the follow-up questions don't have answers. Feynman knew this. He wrote about it. He said, and I'm paraphrasing, "If you think you understand quantum mechanics, you don't." He spent his whole career making peace with the fact that physics works beautifully and precisely, while sitting on top of a mystery nobody can crack. That's not a failure of physics. That's actually what makes physics worth doing. Because when the math still works, but you can't picture what it means, that's where new physics gets born. So next time someone tells you Newton explained why things move, you can smile a little. Because the deeper answer, the one Feynman fell in love with as a bored kid in a Brooklyn classroom, is that nothing really moves the way we think it does. Every particle in the universe is, right now, in some sense, exploring every option it has. And the world we see is the leftover. That's the principle of least action. That's what Mr. Bader showed Feynman. And that's the question your physics teacher quietly walked past. If your brain is still working after that, drop a comment. Tell me, do you reckon the universe is genuinely trying every path? Or is it just a calculation trick? I read every comment, and the discussions on this channel are honestly some of the smartest on YouTube. Next video, we're going somewhere even weirder. What actually happens to you if you fall into a black hole? Spoiler, the answer's not what your physics textbook says. If you got something out of this, smash that like button. It really does help small Aussie channels punch above their weight. Subscribe if you want more honest physics. No jargon, no flexing. And I'll see you in the next one. Stay curious.